Hi everyone, today my group and I will talk about beyond 5G as enabling technology for building smart ports. Smart ports are the ports that integrate smart technologies such as leveraging on AI and big data for predictive analysis on ports' day-to-day operation and Internet of Things to provide ports with connectivity and real-time tracking of the ports. By using smart technologies, smart ports are more operational, efficient, economic competitive, and also have more effective labor management. Beyond 5G technologies play a major role in ensuring the quality of service of smart ports. Since an ever-ready infrastructure to support such application is crucial for smart ports to run effectively. Throughout this video, we will understand the different beyond 5G technologies that enable smart ports.
Like aforementioned, inefficiencies of traditional ports connected via cables have led to the development of smart ports that applies virtual reality, smart guided vehicles, intelligence automation, AR or VR, digital twins, IoTs, and sensors, all which are very bandwidth-hungry applications. As the exponential rise in demand for wireless communications are showing no signs of slowing down, and future applications further accentuating the need for bandwidths, several hundreds gigabytes per second to several terabytes per second transmission rates are required to ensure quality of service, which can only be provided by beyond 5G technologies such as the implementation of Terahertz Waves with the aid of MIMO, OTDS, and rate splitting technologies. All these technologies will be covered later on in the video. Up until 4G, commercial communication was limited to 6 GHz cellular bands. With 5G came a new paradigm which features the use of millimeter waves, and this had showed a major leap by offering hundreds of times more bandwidth compared to sub-6 GHz bands. However, 5G is predicted to slowly reach its limits and is unable to provide the needs of greater bandwidth, fast uploading and downloading speeds to emerging smart ports and cities. One of the architecture change we discovered during our research is the change in the transmission medium. A new wireless transmission medium is introduced, the Terahertz Waves. Terahertz waves are waves between microwaves and infrared rays, which ranges from 100 GHz to 10 THz. Terahertz waves open up much more spectrum capable of supporting up to 1 TB per second data rates in comparison to millimeter waves, which only allows up to 10 GB per second. Due to terahertz high frequencies, it has high path loss, low penetration power, and low transmit power, thus unable to travel long distances. This, however, increases security as the need for directional beams and short propagation distances reduces chances of eavesdropping. Despite the weaknesses of terahertz waves, the potentials that these waves hold are great enough to drive advancement in technology and break through the limitations, making it feasible for commercial deployments. One of such technologies is the recent researched MIMO systems.
According to wave propagation theory, terahertz waves have higher attenuation of the signal in comparison with millimeter wave. Therefore, it only can transfer data for a short distance. To resolve this limited coverage problem, the massive MIMO has been adopted to make the antenna beam more directive in order to cover a longer distance. In a classic case of massive MIMO, the base station antennas are distributed within each cell, and they only serve the users within their cell respectively. To further improve the connectivity of devices, a new concept, cell-free massive MIMO, is proposed. In this type of MIMO, there is no concept of cell or cell boundary, as all the access points are spread across the entire area. And yes, it can support up to terabits per second. Due to the architectural difference, the classic MIMO will experience interference between the neighboring cell, while cell-free does not. Besides, the edge users of classic MIMO will receive a comparatively low quality service because they are far from the center antennas, while the users of cell-free MIMO receive uniform service quality no matter where they are. Therefore, it is said that the cell-free massive MIMO can provide a 90% improvement in data transmission. To increase the capacity and spectral efficiency of the MIMO system, the orthogonal time-frequency space (OTFS) should be deployed in a beyond 5G smart pod to replace the conventional modulation techniques, or FDM. This is because OTFS require fewer cyclic prefix to achieve a shorter transmission time. In addition, another big advantage of using OTFS is that it is not sensitive to Doppler effects, while FDM degrades significantly even under a small Doppler effect. This allows high mobility system to be built in a rural or aerial environment where the Doppler effect may be large. In other words, OTFS is extremely suitable to be used for data transmission in a smart pod.
In order to efficiently cope with the high throughput and massive connectivity requirements of multi-antenna wireless networks in SmartPod, multiple access and multi-user communication system design need to depart from conventional interference management strategies, namely fully trained interference as noise. This architecture can incur some significant loss if the multi-user interference is not within the noise level. On the other hand, rate splitting split messages into common and private parts and encodes the common parts into one or several common streams while encoding the private parts into separate streams. The streams are pre-coded using the available channel state information at the transmitter, superposed and transmitted. Or the receiver then decode the common stream, perform successive interference cancellation, and decode their private streams. Each receiver reconstructs its original message from the part of its message embedded in the common stream and its intended private stream. The key benefit of rate splitting relative to other techniques is to flexibly manage interference by allowing it to be partially decoded and partially traded as noise. This enables rate splitting multiple access to softly bridge the two extremes of fully decoding interference and trade interference as noise, as well as providing room for spectral efficiency, energy efficiency, and quality of service enhancements, and complexity reduction. In general, technologies including Terahertz Waves, multiple input, multiple output MIMO, OTFS, and rate splitting mainly contribute to three aspects of realizing smart pods. Firstly, they provide greater bandwidth. As the number of IoT devices in smart pods increases, greater bandwidth is required so that the devices can be online simultaneously to create a digital twin. Secondly, these techniques can increase output speeds, where largest files need to be uploaded to cloud storage to store real-time data from the smart pods. Lastly, they offer faster download speed to support extremely high-rate information showers, such as holographic communication, tactile internet application, and immersive media such as VR or AR technology.
In transforming from 5G to B to 5G, it's particularly important when it comes to network security. It's important to protect SmartPod's cybersecurity as it is controlled by technology and moves up to 90% of its imports and export items worldwide. Failure to do so will cause a huge economic setback for the country. So now let's investigate where we should improve the architecture model to ensure network security. In 5G, we can investigate these security threats that are present on time. These include DOS attack, which flood a particular network with high traffic, IP address spoofing, man-in-the-middle attack, as well as the unauthorized access for the network layer. So, what is the existing problem with the architecture? As you can see, those are the architecture in the network layer in which possess to both privacy and security threat. In the IPsec, which is an protocol, although it can protect the layer from its authenticity and integrity, but it needs to work together with other protocols as well to ensure the full security. The architecture models such as network function virtualization, network slicing, and information-centric networking have their own vulnerability in terms of facing network layer common attack. Now, a new approach is suggested to further protect the architecture in the network layer, which is the machine learning approach. Generally, it uses deep learning in analyzed data and able to smartly detect potential threat without explicitly code for the network layer protection. So now, there are a few types of machine learning approach in which enable the protection of the network layer. This includes supervised learning, unsupervised learning, as well as reinforcement learning. These three types of machine learning approach are suggested in beyond 5G in order to protect the network layer. As a result, here are the benefits when network layer is secured. It enables the greater efficiency in transporting, as it have a lower port interruption that caused by the security issue on the technology. Data encryption also important to ensure all the customer details such as the home address as well as the phone number is well protected in the smart port system.
One of the many challenges we face in order to make smart ports a reality is the fact that there will potentially be latency issues down the road when using single-path TCP protocols in a multipath communication environment. As such, a proposed solution to this obstacle is to potentially apply the Multipath QIC. QIC is an emerging and new transport layer protocol that provides encryption, stream multiplexing, and low latency data transfer. The proposed Multipath QIC allows us to further enhance its already advanced features by utilizing multiple paths as compared to the traditional TCP UDP protocols that are single-pathed. QIC provides low latency encryption due to the fact that the cryptographic information is shared together with the transport information in a single handshake. As such, with Multipath QIC, it might very well be possible to establish QIC connections with virtually zero RTT data delay. Aside from that, QIC allows stream multiplexing to be carried out, which is essentially the capability to handle multiple requests and responses simultaneously on a single connection. On the other hand, Multipath QIC would allow more request-response pairs to be run simultaneously on a multipath connection instead. In terms of download times, file transfer speeds when using Multipath QIC is considerably higher than when using MPTCP. And with that, the proposed changes, the latency of B5G would significantly be less than the latency of 5G currently, which holds an approximate latency of 10 milliseconds. In a smart port setting, machines and sensors can almost have instantaneous data transfers, almost akin to having human operating said machines in the flesh. Aside from that, more machinery can potentially be operated at the same time when using B5G as a data transmission, as it will be further and faster.
The global supply chain is growing bigger day by day and becoming increasingly digital. Hence, there's a necessity for ports to become a digital node within its territories to handle such amount of shipping traffic. Digitalization is proven to benefit supply chain, customer, and environment by increasing efficiency and productivity through beyond 5G technologies mentioned before, and many others more. Now, let me question you. Among the proposed challenges, which one do you think the operator should prioritize? Secondly, which architecture change do you think will benefit smart ports the most? And lastly, do you think our current technology is sufficient to enable the smart port? If not, please explain. Feel free to comment below. That's all from us. Thank you.